All right, the last topic that we're going to talk about in this section is what's called summation notation. And the idea is if we have a sequence that we want to add up all of the terms that we had just found, we want to get like a sum of all those. It's actually what's called a series. We're going to take all the terms and add them up. Well, you can imagine that if we had to take, 252 terms, you don't want to have to write out 252 terms consecutively or figure them all out individually in a way that it's just really, really tedious and difficult. So we came up with a notation that's going to make things much, much easier. The summation notation looks like this. First of all, the word sum is given by this capital sigma. Okay, and that's what that is. It is a capital letter sigma in the Greek alphabet. That means we are going to add. It means we're going to sum a bunch of things. This number that I'm getting ready to write on the bottom, where it says I equals 1. First of all, I is the variable that we're going to plug numbers into. So this is going to be our variable. Also, I call it the counter, because it's basically telling you what it is you're going to plug a number into. And 1, the 1 part, simply tells us that's where we're going to start. Start with that number. Well, unless we're going to do this infinitely, and there, believe it or not, there is a way, which we are not going to cover here, but we need to come up with a way to stop it. Let's go here. So this number that I'm going to put on the top is where we stop. So this tells us where to stop. So what this means is, whatever I put on the right side of the sigma, and I haven't put anything over there yet, but whatever I put on the right side of the sigma, I'm going to start with I equals 1, then I'm going to go to I equals 2, I equals 3, I equals 4, I equals 5. Basically, it's telling us how many terms or what terms I'm going to be finding, all the way up until I get to 18. When I get up to the 18th term, I plug in 18, then I stop. So, in other words, if I were to put over here A sub I, what this technically means is, okay, the sum of this is A sub 1. I just started with I equals 1. But now I have to do the second term, the third term, the fourth term, the fifth term. I'm not going to write them all out, all the way up until I get to the 18th term. I'm going to take and plug 1, 2, 3, 4, all the way up to 18, all the way until I get my sum. So it would be 18 different terms. But again, this notation is just a shorthand notation. So when you see that capital Greek sigma, it means you're going to sum. When you see the number on the bottom, it tells you what you start with. That's going to be the first thing that you plug in to find your first term. It doesn't have to start with I equals 1, by the way. It could start with I equals 7. It could start with I equals 2. It could be any whole number. It cannot be a negative. It could technically start with I equals 0. There is such thing as a 0th term. We won't be dealing with that here. But just know that that's where you have to start, because maybe I'm not really interested in the first 18 terms. Maybe I'm only interested in, maybe the 10th term through the 12th term. So just 10, 11, and 12. That's all I want to know. So then you would just plug in 10, plug in 11, plug in 12, and then add them up. So let's go ahead and take a look at a couple of examples. Okay, our fifth example, we're going to just take a couple of sums. So they're going to be giving us the sum. There's our sum notation. I is going to start with 1 and go to 6. And what we're going to be plugging that into is I squared plus 1. So what does that mean? That means if I start with I equals 1, I'm going to plug 1 in for I. So my first term is going to be, I'm going to write this below because I'm going to run out of room. It's 1 squared plus 1. That's the first term when I plug in I equals 1. Plus, because that's what the sigma means. It means to add. Now I'm going to plug in 2 for I. So that'll be 2 squared plus 1. Plus, now we'll plug 3 in for I. 3 squared plus 1. We're going to do this all the way until we get to 6. So we'll have 4 squared plus 1 plus 5 squared plus 1 plus 6 squared plus 1. Okay, that's what this means. So let's go ahead and figure these things out. It won't be too bad, I don't think. 1 squared is 1, so 1 plus 1 is 2. 2 squared is 4, so 4 plus 1 is 5. 3 squared is 9. 9 plus 1 is 10. 4 squared is 16, plus 1 is 17. 5 squared plus 1 is 25, plus 1 is 26. And 6 squared is 36, plus 1 more is 37. And then if I was to go ahead and add all these things up here, a little quick mental math. I don't expect you guys to do it that fast, but you get 97. So that would be the sum. So this thing right here has a sum of 97 for the first 6 terms, I equals 1 to 6. Okay, let's do another one. Let's do the sum. I equals, actually let's change the variable because the variable can be changed. I want to make sure you see that. This part down here, it doesn't matter what variable they put in, you just need to know that that's what you're looking for in the sum. So k equals 4 to 7. Notice that does not start at 1. And we're going to do negative 2 to the k power minus 5. All right, so let's figure out this sum. So this time we start with 4, and that's the important part. We have to start with 4. So we're going to have negative 2 to the 4th power minus 5. That's the first term. The next one is if I plug in, because now the counter kicks up by 1, I got to plug in 5. So it'll be negative 2 to the 5th minus 5. And then we got to add the next one, which is going to be negative 2 to the 6th minus 5. And then the last one should be negative 2 to the 7th. Squeeze this in there, minus 5. There we go. All right, so these numbers are going to start to get a little bit bigger because of the values that we have. So negative 2 to the 4th power is negative 2 times negative 2 times negative 2 times negative 2. That's 16. So 16 minus 5. Negative 2 to the 5th power is going to be 32, but it's going to be negative 32 because it's an odd power. So it's negative 32 minus 5. Negative 2 to the 6th power is positive 64 minus 5. And then negative 2 to the 7th power is negative 128 minus 5. And then adding all these values up, let's see, we can add up the insides pretty easily. That's 11. That's negative 37. 64 minus 5 is 59. And negative 128 minus 5 is negative 133. And if we add all of those things up right there, we are actually going to get negative 100. Actually kind of works out nice. So there's your sum, but this is the sum when k started with 4 and only went up to 7. So we only actually had 4 terms that we had to deal with there, although they created some slightly bigger numbers. Okay, one more example, and then we're actually going to be done with this section. So let's do letter C. So we'll do one more sum. This one's going to be a little bit different as well. We'll go back to I. I equals 1 to 5 of 3. So what you should notice here is, remember I said you take the numbers at the bottom of the sum notation, you plug those in for all of the i's. The problem is 3 does not have I in it. There's no I in it whatsoever. So if I was to start with the first term of this sum is 3. But when I kick the counter up to 1, if I plug 2 in, well, there's nothing to plug it into, so it's just another 3. And then when I move to I equals 3, there's nothing to plug it into, so it's just 3. And then if I go to I equals 4, there's nothing to plug that into, it's still just 3. So really what that means is I am adding 3 5 times, because there's nothing for me to plug the I into. It's just what's there. It's 3 plus another 3 plus another 3, 5 different times. And of course 3 plus 3 plus 3 5 times is just 15. So just be careful when you see a constant and there's nothing to plug the numbers into. You just add up that constant however many times you need to get from whatever the starting number is to the ending number. And that's how you get your sum.